Hello, calculus fans! Let's evaluate the integral from 0 to 4 of dx over x minus 3 quantity squared. Now, the very first thing you should notice is that the integrand is discontinuous at x equals 3. Look what happens when we plug in x equals 3. We'll get a 0 in the denominator, and that's exactly what makes this thing discontinuous. Now that value of 3, where we have our discontinuity, that's inside the interval from 0 to 4. And so, we're going to break up the integral. You know, if that discontinuity happened outside of our bounds of integration, like let's say the discontinuity was at 5, we wouldn't care at all. We would just charge ahead and use the fundamental theorem of calculus. Here, the discontinuity is inside, we got to worry about it. So to break up this integral, we'll write it as the integral from 0 to 3 plus the integral from 3 to 4, because that's where our discontinuity occurred. All right, we're going to evaluate these integrals separately. First we'll do this one, and then we'll do the integral from 3 to 4. Okay, so let's evaluate the first integral. So we have the integral from 0 to 3 of dx over x minus 3 squared. Because it's an improper integral, we have to write it as a limit. No choice in this matter. It must be done like this. So we write it as a limit as m approaches 3 from the left of the integral from 0 to m of x minus 3 to the negative 2 power. Notice I rewrote it, so instead of an x minus 3 squared in the bottom, I wrote it as x minus 3 to the negative 2, eliminating the fractions. And now this is actually a fairly easy antiderivative. An antiderivative is just negative x minus 3 to the negative 1. You can just use the power rule, and then the chain rule is not going to cause any problems, so we don't have to make any alterations. And so now this is a limit or the bounds of integration go from 0 to m. We plug those in, and if we evaluate the limit, we can see that the denominator of this dude here is going off to 0. So the whole thing is going to be going to infinity. Now what that means is that first integral is divergent. And so that means the original integral is divergent. There's no need to evaluate the second integral. If we have to break up an improper integral into two pieces, if one piece is divergent, then the whole integral is divergent, and so we don't even need to go evaluate that second one. It doesn't matter. So we're done with the problem now. I would also like to point out that it's very, very important to not just blindly evaluate this original integral using the fundamental theorem of calculus. All right, here's what it might look like. If you did not recognize this as an improper integral, you might just do this, evaluate the integral by writing down an antiderivative and then plugging in the 0 and 4, and you'd get some numbers and you'd get an answer. You've made a huge mistake. One of the hypotheses on the fundamental theorem of calculus is that the integrand must be continuous over the entire interval of integration. If that hypothesis is not satisfied, then we cannot use the fundamental theorem of calculus. In this case, the function is not defined at x equals 3, so we cannot integrate that over the entire interval. That's why we have to break this up. The answer of negative 4/3 is simply not a right answer. Okay, that's all for now.